Hi everyone, Mr. Lee here. In this video, we're going to go over electric potential energy. Now, as a quick reminder, electric potential is not the same as electric potential energy. Electric potential energy has the units of joules, whereas electric potential has the units of volts. Okay, so let's just do a quick little recap of electric potential. So volts, or the voltage of a charge distribution. Now, volts, or the electric potential, can be thought of as the height, whereas the electric potential energy is the amount of energy stored within the field at that location. It's how much work that charge can do at that one location. Okay, so before we go on, what I want to do is I want to do a quick analogy. Once again, we've been trying to explain potential by using the mechanics version of energy, right, and the gravitational field. So this will be no different. We will use the same idea. Let's begin. Now, let's say we have a floor, right? This is the Earth, and the Earth has its own gravitational field, and the Earth's gravitational field is pointing downwards. This is very important. Now, when the gravitational field is pointing downwards, and we put a object, let's say it's a beautiful red ball within that gravitational field, and we drop it, we expect the ball to drop to the floor, right? Now, if we were to describe what just happened in terms of potential energy, here's what we can say. We can say that at the initial position, the initial potential energy, let's make that a little bit smaller, okay, is up here, and we can say down here we have the ball. When let's say that it just like lands on the floor. When it lands on the floor, we have a final potential energy. Okay, so there's a change in potential energy. Now, how do we know this? Well, if we take a look at the potential energy formula, let's erase these gravitational field lines. We don't need that. We can see that potential energy, or the gravitational potential energy, is equal to mg and h. Now, what's important here is that if we have a change in gravitational potential energy, we have mg delta h, or a change in the height. And so because the object changed its height, we know that the gravitational potential energy has changed. Now, this is important because if we were to go over the idea of work, what does work? There's a couple of things that I need you to, I guess, like recite every time we come across these problems, all right? I want you to think about what is quote unquote normal, what is natural, right? What is expected to happen, because that will actually help us out a lot. So what I mean by that is if we were to drop this ball from a height, we expect it to fall, okay? That is normal. Now, whenever things are quote unquote normal, we say the field does work. Now, in this case, the field is the gravitational field. The gravitational field is doing work. And we come across the equation of work is equal to the negative change in potential energy, whatever that might be. Okay? See, so whenever it's normal, the field does work. Now, if we were to take a look at this numerically, we can see how this equation really plays out. So for example, let's say up here we have a potential energy of, let's use easy numbers, 10 joules, and down here we have a potential energy, because it touched the floor, actually let's do it right before it touches the floor. We'll say 1 joule, all right? Now work is equal to negative delta U, and delta means final minus initial, so we do UF minus U initial. So if we take a look here, UF would be 1, U initial will be 10. 1 minus 10, that gives us negative 9. Okay? So, negative 9, and of course there's a negative in front of it. So this turns out that the field did 9 joules of work. It works out. Aha! All right, so you might be thinking, all right, well, where did that energy go? And if you're not asking yourself that, you should be asking yourself that, because that actually helps out with these problems. You need to be always asking, according to the conservation of energy, energy cannot be created nor destroyed. It goes from one form to another. So when the gravitational field did work to this object, where did that energy go? And the answer is the potential energy that was stored within the field got turned into a form of kinetic energy. All right. And that is what we see here. Okay, now what about the opposite? Right, so this is what's natural, right? Natural is this object falls down and the object, well, you know what? Let's in fact write that down. Not only does the object fall down, but it has an increase in kinetic energy, right? It gains some form of speed, and the form of speed increases because there's a force that is accelerating this object. So the velocity is increasing, it's faster, faster, and faster. This is normal. Once again, you have to ask yourself, what is normal? All right. Now, what about what is not normal? All right. So when not normal things happen, that means there is a outside external force. For example, we should not expect a ball to just float up into the air. Okay. We can expect that balls can fall down, but we cannot expect balls to rise up. So when something like that happens, it must mean that there has to be an external force that has caused that motion, such as a person. So I'm going to draw a face here, right? Let's say this person, hello, right? This person has a red ball, okay? And that person, they extend out their arm, whoop, right? And they put that red ball up here. Of course, this is not drawn to scale. That would be really freaky. All right, so if the person raised that red ball up to that height, we can say that the person did work. Now, let's write this down. We're talking about things that are normal / not normal. And when things that are not normal happens, that means that there is an external net force that has occurred. So in this case, the external force caused a work to be done to the object. So the work external added energy to the system. Okay, this person added energy to this ball, and this ball gained energy, and that energy is now in the form of potential energy stored within the field. All right, so during that motion, what happened? What happened with the field? Well, you got to think about it. So if we have a ball, right? So let's do a ball right there. And let's do a free body diagram. The first force that we should draw is the force of gravity going down, aka the weight. And here we have the force of the hand pointing up, right? Or the normal force of the hand. Now, let's say that the ball is moving up with a positive velocity. And the reason we say that is just to make things a little bit more simpler. Because if there is a positive constant velocity, that means there's no external forces. Because the acceleration is 0. That means the force of the hand and the force of gravity, they're the same. All right, so if the ball is rising up and the two forces are the same, this is what we can say. The force of the hand does positive work. Okay, the force of the hand is doing positive work to the object, but the force of the gravity is doing negative work. It's going against it. And this is, this goes back with the formula for work. If we take a look at the formula for work, we say that work is equal to force times the displacement, but there is a special trig function that we can add at the end. And that little trig function is the cosine of theta. Now, what that simply means is that the force and the direction, if they're going in the same direction, so force and direction, same direction, right? So if the force vector and the displacement vector are in the same direction, then we have positive work, such as this ball. This ball is moving upwards, right? This ball is moving upwards, and the force is also upwards. We have a positive work being done. Now, what about the cosine of theta? How does the cosine of theta explain it? Well, if we take a look at the two forces, or the two vectors, we have F, and we have here delta x. The angle between these two vectors is 0. And the cosine of 0 just gives us a positive 1 value, right? So this means that this work is positive. All right, now what about the force of gravity? What about the gravitational field? Okay, so the gravitational field is doing negative work if this external force is doing positive work. So we can take a look at the equation. The gravitational force is pointing down, the displacement is going up. So this angle in between, that is 180 degrees. So the cosine of 180, right, also known as the cosine of pi, is -1. And negative 1 times F times delta X gives us negative work. So this shows us that F of G is doing negative work. The gravitational field is doing negative work. Now, the best way to approach this is to just simply think, is the object doing what it naturally, normally wants to do? And if the answer is no, that means the field is doing negative work. If the object is doing what it naturally, normally wants to do, that means the field is doing positive work. All right? Very important. So how does this relate all to particles and electricity? Okay, so let's take a look at it. Let's create a scenario. We'll create an equal potential scenario. So I'm just going to do a quick little box. Let's make this here. Let's make this 0 volts. Let's make this here 1 volt, and let's make this here 2 volts. And this little section here we can say is 3 volts. All right. So these are our voltage lines. Now, what is not included is the field lines. Okay, I did not draw the electrical field lines because that's part of the process of really determining what's going on here. So what you should figure out is, where is the positive charge? Where is the negative charge? So if I take a look at this, you got to remember, the closer we get to the positive charge, the positive voltage increases. So it is safe to assume that we have a positive charge somewhere there that is causing these voltage lines. Now, the next step, after you identify where is a positive charge, you have to think to yourself, well, what about the field lines? Well, if the positive charge is there, then that must mean, I'm going to erase these in a little bit, that must mean that the positive field lines are coming out like so. And that's important because we need to be thinking out about the field lines and the charge itself and what is normal / natural. You know what? I'll leave that up there. Okay, so here's a question. We're going to come up with different locations. So the first location we will say is here, A. The second location is here, B. Third location, we'll go up there, C. And the last location is down there, D. I want to be able to answer this conceptually before I introduce to you the formulas. All right, so we have to think about it. If we have a positive test charge, right? We have a positive charge, and that positive charge is at location A. We'll start off at A. All right, so we have a positive charge that's at location A, and we move the positive charge from A to B. Okay, we move A to B, and the question is, how much work is being done? All right. Now, we have to really think about this and go back to this scenario up here. In both of these scenarios, remember, the green line is the field lines. Okay, and what I didn't draw were the height lines. So I'm going to do that right now. Let's say right there, that's a height of, I don't know, 20 meters. All right, and right down here, we'll say it's a height of 10 meters. All right, now there is only a change in potential energy if there's a change in height. Okay, and that comes across right there in the formula. Therefore, there is only work done if there's a change in height. Now, let's use our analogy here. We said that voltage is a lot like height. Therefore, we can replace the word height with voltage. There is only work done if there is a change in voltage. Therefore, if we move the ball from location A here to location B right here, no work was being done because there was no change in height. So if we were to take a look down here, okay, if we were to go from A to B, and so that we can write this out, voltage A is 1 volt and voltage B is 1 volt, there's no change in voltage. Now, because there's no change in voltage, the work from A to B is 0 joules. If you move along the equipotential line, there is no work required to move along the equipotential line. Okay. Now, another way that we could think about this is by using the mountain analogy, right? So if you're right here at the mountaintop, we'll use a different color. If you're right there at the mountaintop and you want to move up the mountain, that requires some work, okay? Now, let's compare that to you're at the mountaintop, but there's a nice little path, and that path is just along the same height, so you don't have to go up the incline. So you just go from one side of the mountain to the other. Okay, nice easy stroll. Because there was no change in height, that didn't require any work. Okay, so think about it like that. All right, now what about from, let's go from A to C. All right, now let's think about what is natural. We have a positive charge, and we are making this positive charge go towards this positive charge here. Okay, we're going against the field lines. We have this positive charge and it's going against the field lines towards the positive charge. Like charges don't want to be near each other. We are causing it to do something it does not want to do. Therefore, we can say that for here, that the work done by the field, aka the E field, is going to be negative. Therefore, what this means is that there must have been a work done by some external source, and that external source will be a positive amount of work done. Okay, so what about from the work from A to D? All right, so now we got to think about it. We're going away from the positive source. Okay, we have a positive charge, and that positive charge is going away from this this big positive source here. Okay, it wants to do that. So because it's doing what it wants to do, we can say that the work done by the field is positive. And there we go. The work done by the field is positive because the charged particle is doing what it wants to do. All right, now let's introduce to you a formula. So there's going to be a couple of things that we can use here. The first one is the work formula. Work is equal to force times the times the displacement. Okay. Now I'm just going to simplify this up and just say like F times D, right? And of course, there's a cosine of theta, but that cosine of theta simply is there to help us identify if we have positive or negative work. But now we have a new method, right? We can now think about what is quote unquote natural. And on the other side, we have negative delta U, right? Which is a change in potential energy. Now, we can also say that F is equal to EQ. So this is, if you remember, for this formula, this is a charge in a E field. Okay, so we have a charge is in an E field, and in order, so when a charge is in a E field, it'll feel a certain force. So what we can do is we can put that into our equation here. We can say EQ times the distance that the charge moves. So if we have a charge in a field and that charge moves a certain distance, work is done. It might be the work done by the field, it might be work done by the external source. Only you can really tell based on the scenario. Another way that we can write the work equation is by looking at the scenario that we did before, right? If we have a charge and that charge moves around or between voltages or a potential difference, then we know that work is done. All right, so let's try it. I'm going to use this equation here because we have all the variables. Let's just say that the charge that we're dealing with, we'll make it easy for us. We'll say it's 1 coulomb. All right, let's do it from A to B. So if we're going to start off with the original equation, 1 coulomb, final minus initial. Our final was 1 volt minus 1 volt. 1 minus 1 gives us 0, so the work done was 0 joules, right? Boom, checks out. Okay, now let's go from A to C. Now let's quickly remind ourselves the work done by the field is negative, and therefore there must be a external work that was done, right? So W is equal to Q delta V. We say that our Q was 1, and our we go from A to C. C has a voltage of 2 minus 1. Okay, 2 minus 1. So this gives us a total of 2 minus 1 is 1, 1 times 1 is 1. So the work done was positive 1. Now hold on. We said that the work done by the field was negative and the work external was positive. So if we extend this equation out, negative delta U, we can divide both sides by negative, right? And we get the work field. I'm going to zoom in there. It's kind of hard to see, isn't it? The work field is equal to negative 1 is equal to the change in the potential energy. Okay, but the work external would be the positive 1 joules. Okay, to get it from one point to the other. All right, now what about work from A to D? Now let's remind ourselves the work done from A to D, that will give us a positive work done by the field. So here we have Q delta V. I'm going to rewrite it. Q is 1. Our final voltage is 0. Our initial voltage was 1. 0 minus 1 gives us negative 1. Negative 1 times 1 gives us negative 1. So the work done was negative 1. Now, hold on one second. Remember, we said that the field does positive work. And if you remember, on the other side, we have negative delta U. We divide both sides by the negative. 1 is equal to the delta U. Okay, so we can see that the field has done positive work. So let's do a quick little recap. Okay, now a lot of times students get tripped up on the whole negative. The idea of the negative that is there, the important thing is you have to be asking yourself what is normal. I know I've been saying that throughout this entire video, but that would really help you out in order to identify what is negative and what is positive. Okay, if the charge is doing what it should be doing, that means the field is doing positive work. If the charge is not doing what it should be doing, that means the field is doing negative work, and vice versa. That must mean that there is some other force causing the charge to do what it doesn't want to do. Okay, so as long as you keep that in mind and you apply that to these signages, it should work out. Okay, best of luck. This requires a lot of practice, but with a little bit of practice, we'll get there. I'll see you next time.